Welcome to the John R. and Donna S. Hall Engineering Lecture. Over the years you have, let's see. Over the years you've heard me say a number of things about John Hall, for whom this lecture is endowed along with his wife Donna. Of course, he was a graduate of the School of Engineering, is a graduate of the School of Engineering, first academic All-American, graduated with honors. Served on our Board of Trust and served as the chair of the Board of Trust of the university. He and his wife, Donna, have been really dedicated to Vanderbilt, but also they're very, very dedicated to Kentucky and to the Appalachian region, such that when Kentucky Educational Television made a documentary about John Hall, they titled it the Kentucky Commodore. John and Donna most recently did a ribbon cutting on a softball field at a university in Kentucky that they endowed. They are major benefactors for the arts and education and community things. They also, of course, do love Vanderbilt and love engineering, and such that when John stepped down as CEO of Ashland Oil after 40 years there, the Ashland Oil Company and their foundation endowed the John R. Hall Professorship in Chemical Engineering that is held by our own Peter Cummings. And I am pleased to say that Peter will be assuming responsibility for the Hall lecture after this one. Today's lecture is a part of a series of events starting yesterday in celebration of the many activities in partnership with IBM. And I am pleased to say that today we have with us Dr. Naguib Attia, who is Vice President of Global University Programs for IBM, and whose son was one of my students several years ago. We also have Kimberly Green Starks, Lee Wilson, and Steve Payman, also with IBM. And of course, we are pleased that today we have our speaker, Dr. Robert Sutor from IBM. Bob is currently the Vice President for Q Strategy and Ecosystem with IBM Research. And as a measure of how valuable he is to IBM, I counted up on his resume, he has held 6 different vice presidencies over the last several years, spanning a range of technologies from quantum computing to AI to blockchain to data analytics, data science, mobile apps and technologies, cloud computing, social media, and a variety of other things. He holds his bachelor's degree from Harvard and his master's and PhD from Princeton. And I am pleased today then to introduce you to Bob.
Okay, let's do the switch. There it is. Okay. All right, so today we're going to talk about the state of the art in quantum computing, which is conveniently done by us. Amazing. So I'm forced, therefore, to use examples from IBM. I'm sorry. Really, I want to give you an idea of why quantum computing is different. If you've heard anything about it, you may have heard terms like qubits. You may have heard some weird, vague statements like qubits can be 0 and 1 at the same time. That's one of my personal ones I hate because there's so much mathematics under that. And this is the School of Engineering, I can say this. You know, it's a linear combination, darn it. You know, it's not just somewhere between 0 and 1. So I'm going to take you through a few things around the motivation of quantum computing, a little bit about how it works, both mathematically and physically. I'm not going to be too afraid to say phrases like Hilbert spaces, but I'm not also going to talk about Hilbert spaces for 15 minutes either. I want to really give you an idea of where we are. One of the things that I am terrified about as we move forward with quantum computing is expectations that are too high. That is, I really dislike it when people say quantum computing will do this. Quantum computing will, my favorite from last week was quantum computing will solve the problem of climate change. Except we don't have a clue how to possibly do that, right? And in fact, there's one little mistake in this presentation. It wasn't from something I made, where it actually is a little stronger and says will. Rather, you should think of all of this as we hope it could possibly, it might, because this technology, while we're doing something with it, and we have some small quantum computers now, it's taken over 100 years to start to be an overnight success. And there are so many significant scientific and engineering challenges ahead, right? Including theoretical physics and mathematics and problems like this. If you start with 1 qubit and 2 qubits and 5 qubits, it's not just a question of building a few more qubits, right? It gets really hard at certain points to add more power to these machines. And I'll give you an idea of how to think about that as well. So the title of this, Don't Count Your Qubits Before They're Hatched, is in part to dissuade you from thinking that if anyone has more qubits at any given time than someone else, somehow they're better or the machine is better. You know, nothing could be further from the truth. 2,000 really lousy qubits are not better than 50 really good qubits, all right? But it takes a little bit different way of thinking about this. This is not version 2 of anything. This is not like, oh, hey, you're really good at classical computing. You've been programming for so many years. You know a lot of algorithms in classical computing. Congratulations, you now know nothing about quantum computing. Okay? And so, it's always good to learn new things, right? And to go back. As I do describe a little bit of a way of thinking about qubit, you'll get this notion of quantum computing, the way they're working together. You're working in much higher dimensions. And even the algorithms, you know, you almost want to imagine as happening in 2 dimensions versus the somewhat more linear approach we take today. So I'm going to start now with a video. And it starts a little slowly. You'll hear some sound, but I know there's no picture for a while, so don't freak out. This is a short video of our Quantum Computation Center. So these machines are in Yorktown Heights, New York. It's about 30 miles north of New York City. This is IBM Research Headquarters. We have 12 labs around the world. This is the traditional headquarters. This building has seen many things. It was erected before there were mainframes, and it has adapted to everything. And our blue gene technology and everything has flowed through this building. And so I'm cutting to the punchline of if you're running a quantum computer, where is that machine and what does it really look like? So let's listen to this for a couple of minutes. That's really cold. Someone has told me that's the same tempo as Queen's We Will Rock You. So if you're tapping your feet, that's why. All right, so let's talk a little bit about why. So 1981 seems like a long time ago to some of you, not all of us. It was the year after I graduated from college, all right? But really, computing goes back to the late 1940s. And a lot of the computing infrastructure was developed because of World War II. But really, computers were great big tabulating machines. And literally, they would be used to produce books of trajectories. So if you're shooting a missile at somebody from a cannon of some sort, you needed to know what angle to go where and things like this. And computers would print out these tables. And so from that perspective, 1981 was really only about 35 years after computers began. And that was 37 years ago, right? So this was roughly halfway back since we realistically started using computers. And so there was this conference that we jointly sponsored with MIT to start asking some very fundamental questions. This was not a computer science conference. In fact, I'm not even sure they had come up with the term computer science at that point. It was to ask what were the fundamental limits of computers. So we build computers of circuits, transistors, semiconductors, and so forth. A priori, is there any reason to believe that the classical computers that have been constructed in time will solve any problem? Right? So if we keep making the processors faster, or add more cores, or add more memory, or add more storage, or increase the bandwidth, is it the case that eventually these machines will get powerful enough to solve anything we really care about? And this seemed to be the case when Moore's law was really in full bloom. Every couple of years, our machines would get roughly twice as powerful. They'd get half as big, and they'd use half as much energy. And life was great, and people kept coming up with more and more sorts of computers. So much to the degree that even if you look at what your smartphone is today, that would have been considered a supercomputer 20 years ago, if you compare the specs, right? Even going back to the iPhone 6, that was 200 million times more powerful than the computers that they used for the Apollo guidance systems to send people to the moon in the 1960s. So we've obviously come a long way, but things seem to have stalled, right? So whether Moore's law is dead or sleeping or taking a detour, whatever, but certainly it doesn't seem to be the case anymore. Now, some of this goes back to these thoughts to even earlier considerations in the 20th century, when mathematicians were asking questions like, all right, if I build up this edifice of mathematics from a series of axioms, right, and I produce theorems and lemmas and corollaries and these brilliant things, are there in fact some true things that I can nevertheless not prove? And it seems kind of weird, right? Because if it's true, you should be able to prove it. But if you really follow logic, they become separate questions. And in fact, Kurt Gödel proved once and for all that, in fact, sorry, there are true things and we'll never be able to prove they're true in any closed system of axioms. So this was a related sort of questions. Can we ultimately compute things with the power? And the answer is no. I'm sorry, but we're simply not going to be able to do everything we ever want to do, that there are some problems or some aspects of problems or some approaches to problems that will never be amenable to classic computers. And so one of the people who was there, and he's about a quarter to a third of the way in the back row, kind of standing by himself, was Richard Feynman, a very well-known physicist, of which there are many stories and anecdotes, of which it seems he made up many of them himself. But he was an interesting guy. Parts of his reputation have not stood up so well to time, but he was a brilliant physicist. And he basically said, look, this classical theory, this constant analysis, is ultimately going to fail. This is, I'm paraphrasing what he said there, was because nature isn't really classical. That is, nature is built on quantum mechanics. And nature does some pretty incredible stuff that we will never be able to handle with classical computers. So this was his colorful way. So for any of you who are running papers in the future, you're allowed to swear in them, thanks to him. And so my example I use is the caffeine molecule. This is one that people know everywhere around the world. And so if you take one caffeine molecule in the lower right-hand corner, it's not a very big molecule, right? And the question is, can we completely describe its energy state? So pick one caffeine molecule at one instant in time and write down everything you possibly can about its energy configuration. How much room does that take up? So the orbitals and all the quantum mechanical information. That would take roughly 10 to the 48th bits. So here I usually say that's 1 with 48 zeros. But that's big. The number of atoms in the planet are estimated to be between 10 to the 49th and 10 to the 50th. So we would need storage in bits proportional, in worst case, to 10% of the size of the planet measured in terms of atoms. So plug for IBM, we make great storage, but we're never going to make storage that big. Okay? Now, we could represent it using these other weird things, these quantum bits, or qubits, as we'll call them, in 160 qubits, and I'll show you why in just a little bit. Now, 160 qubits, I hesitate to rather I don't hesitate, but that's simply the storage capacity. That's not saying what it would take to actually load up that information. I'm also not saying what it would take to compute with it. But I'm saying you could represent that much information. And some other molecules, if you're curious, so water, the same amount of information represents 10 to the 4th. We could represent 14 qubits, all the way down to penicillin, which would require 10 to the 86 bits, or 286 qubits. So something interesting is going on here that we can do this. Now remember, this is just storage capability. We would need bigger computers to do something interesting. I mentioned penicillin because one of the examples that many people talk about is drug discovery, and will quantum be useful for that? Well, we're hopeful, and one of the things that's very true about quantum today is the machines are small. So we have publicly available 5 and 16 qubit machines. You can use real quantum computers. You can also simulate those on your laptop, probably your phone, right? Just to be clear, but if you want to use a real physical machine. So when we talk about applications, nobody on the planet can say, my quantum computer right here can do something that cannot be done on a classical computer. No one can say that today, all right? We think that will change in 3 to 5 years. So we've got a little time for return on investment, right? Yet, because this is so different, it's going to take some time for people to understand what this is, understand how to think about it, and understand how to apply it. It's not going to be one of the deals where you're told on Friday, by Monday, figure out how to do this. It's more likely in 6 months, you'll begin to feel somewhat comfortable, and the next day, you will find out you were completely wrong about one of the fundamental principles. Okay? Quantum mechanics, on which it's based, is one of the hardest and strangest parts of science. So there's no reason to think it's necessarily going to be that easy. There have been religions built around quantum mechanics. This thing I mentioned about caffeine requiring all this information, one molecule in one instant, how does nature tap into somehow making use of all that information, right, compared to physically what we think of as our planet? The answer is we don't know. There are many theories. It makes great weekend reading, right? But during the week, we try to make quantum computing work. So we don't know how the fundamentals work, but quantum mechanics, at least so far, seems to be the way to do this. So as you would expect, chemistry is probably an early area of application. And we have some beginning algorithmic proof that this is likely to be the case. Material science, probably sooner, simply because the structures are simpler, right? Oil and gas, possibly, maybe some of the new catalysts for some of the processes. Drug discovery, maybe, but probably at least 10 years, maybe 15 years if it happens. And what I mean by that is the machines will be large enough to both somehow model the drugs exactly and how they interact with other molecules, such as those in your body, right? So there's a difference between drug discovery and drug computation. Can I create exactly the drug, so-called customized or personal, pharmaceuticals for you to do a certain thing? So this is only saying what we will need, not exactly how to do it, right? But the capability. AI comes in two flavors. This is slightly overhyped today. Quantum computers are not big data machines. You cannot push a lot of information through them. So think of them as being customized for certain types of computations, particularly computations that have a relatively small number of inputs, but that once you are working, they would blow up exponentially inside the actual algorithm. So on one hand, we say, are there existing AI, specifically ML, DL algorithms that down deep we could improve the speed of some linear algebra operation, probably matrix inversion using quantum? So can quantum help what we do today? On the other hand, we might say, can we come up with completely different algorithms, right? Different approaches, different perspectives on how to do some things like classification, right? By taking advantage for particular data sets, relationships in the data that somehow we can model using entanglement among qubits in the algorithm. So that is a very sophisticated view of understanding specifically the structure of the data as well as whatever your algorithm happens to be. Most people, probably nobody, has that sort of insight today. And then financial services. There, it's starting to pick up, right? Why is this interesting? So there's the old joke, why do people rob banks? It's because they have all the money. Why are companies interested in financial services? Well, they invest, and they invest in new technologies. No one wants to rob them, just to be clear. I'm not suggesting that, okay? But they are very interested in cutting-edge technologies. So for risk analysis, right, they do Monte Carlo simulations where they are doing millions and millions of samples in order to try to build a big model, in order to do pricing, in order to evaluate risks, such as value at risk, conditional value at risk. How efficient are these Monte Carlo methods? How well do they actually model the true space? So even if we think of a very simple distribution, more of a Gaussian distribution, the Monte Carlo methods aren't that especially good at measuring what's happening in the tails. So that is, can we somehow do a better job at rare event simulation than we can with traditional methods? And beginning papers like this out of Zurich gives us the sense that the answer is a strong possibly, okay? And I show it here in case you want to find it as well. So as I've stressed, we are not at the point where quantum computing is showing a demonstrable advantage. So a demonstrable advantage says, right over here, a quantum computer can do much, much better than any known way we can do it on a classical computer. That's what we call quantum advantage. Now, we're sort of hedging things a little bit because I said any known way on a classical computer. If you come along and come up with a much better way on a classical computer, that advantage may shrink, right? And so people are always hoping to try to come up with proofs that show that this particular algorithm, reaches or is much closer to a theoretical minimum or maximum or something like this. By demonstrable advantage, I mean 1,000 times better. I mean, who cares if it's twice as good? Run it twice as long and you're done, right? Computing power is cheap enough to do that. We would really measure this in other terms. We'd measure it in terms of, is it a quadratic improvement? Is it possibly, the hope for exponential improvement, as we've seen in a couple of examples. But today we're in this quantum ready phase. So we have some quantum computers that are available. We have the foundations for programming. We have software development kit that you can use. You can get up and running and using it today to start to figure out what the heck this is, and as I said earlier, even if you're a great classical software engineer or programming, how you have to start adapting the way you think to make use of quantum. All right, so that's where we are today. We hope to reach quantum advantage in 3 to 5 years. So in the 2020s, 3 to 5 sounds fairly reasonable. Okay, so let's talk a little bit more about this elusive qubit. As far as I know, there are no good explanations of what a qubit is. All right, I am a mathematician by training. Those definitions are great, right? So we can talk about two-dimensional complex Hilbert spaces. It's a vector space with a norm, all right? And we can talk about tensor products. We can talk about entanglement and what that means in terms of tensor products. And I'm really cool with that, right? It's nice to fall back on to really know what's going on. However, half of those words I just used, I cannot use with most people, right? So we have to wave our hands a little bit more. And so therefore, you will see examples of a spinning coin, right? So somehow, the coin is spinning, and when it stops spinning, it will be heads or tails, and that's your 0 or 1. And so that's how people sort of say, well, you know, it's 0 and 1 at the same time, because when it's spinning, you don't really know for sure, right? But when you poke it and it falls down, it's 0 or 1 at the same time. All right, that's sort of okay. There's also the spinning donut variation on that, which if you're more of a foodie, maybe you'll do that. A little bit more rigorously, we might say that on the bottom there, that a qubit is something that lives in a two-dimensional complex vector space. So the two dimensions alpha and beta are complex numbers, all right? There are two basis elements, which just for the sake of labeling, I will call 0 and 1. Do not think of them as the integer 0 and the integer 1, okay? I'm just going to call them 0 and 1. Okay, well, that's sort of interesting. And oh, by the way, this thing has norm 1. All right, so that whenever I tell you that there's some combination like this and it has norm 1, it lives on something spherical, a circle, a sphere, or something higher dimension. That's what that really means. Okay, now this is a complex number. And so alpha and beta each have real and imaginary parts, so that gives you the impression it's maybe a 4-dimensional space. However, because of the restriction on the norm, and because of a projection onto the surface of a sphere and forgetting about certain rotations, in fact, I can map all the values that the qubit can take on to something called the Bloch sphere, which is what I'm showing on the right-hand side, B-L-O-C-H. And so here we will label, somewhat arbitrarily, the North Pole as 0, again, and the South Pole as 1, okay? You have to forget about certain things like being orthogonal and whatever, but let's just kind of go with it for a while. The values that the qubit can take on, while it is in use, can be any point on the surface of a sphere. So a bit, in contrast, is 0 and 1. Only one of those. It's 0-dimensional, right? So 2 points, 0-dimensional. Whereas this lives in a 2-dimensional space. 2-dimensional real space in this case, that's projected onto the surface of a sphere. So a qubit, when it is in use, right, has a lot of elbow room, 2 whole dimensions. It can move anywhere around. And so what you're actually thinking about as quantum operations on this qubit are moving points around on the sphere through unitary operations, right? So these are reversible operations with certain characteristics. That's what a qubit is, okay? Go and compute, right? Now, physically, down here, what I've shown is a 5-qubit machine. And so these little squares, those are the actual qubits that we implement. Now, what I previously showed you with the Bloch sphere is a nice and elegant, real way of talking about it. That is a physical qubit. Physical qubits are imperfect. There's noise that goes into them. They are actually analog devices. They don't work perfectly, but they work fairly close enough. And so I'll use this phrase again. The whole point is to make these as good as possible, to make some very good ones. So in terms of some of the differences now, with a classical computer, like in Moore's law, we would need to double the number of transistors to double the power, more or less. Right? There's some overhead, but that's about it. With a quantum computer, you simply have to add one more qubit. Now, there are engineering and physical constraints on how you actually do that, right, and still have something that works well. But that's the theory. So going back to our math here, if you remember, so when we have one qubit, this is what it looks like. So we have our alpha and beta, right? And here we have things that look like 0 and 1. So we have two complex numbers. So their alpha and beta are two things, 2 to the first. Let's add one more qubit. And now we're adjusting our notation, and it's beginning to look a little bit less like just 0 and 1. We've actually taken a tensor product in here. But we go from all right, let me say it straight out. We go from a vector space of 2 dimensions to one of 4 dimensions, and we've constructed the basis elements from the basis elements of the previous one. So there are combinations like this. And we have A, B, C, and D, which is obviously 4, and 4 is 2 squared. So the big question is if we do this again, we have two choices of what's going to happen. Are we going to go to 6? That is, are we just going to add 2 more? Because that's what happened so far. Or are we going to double? And the wonder of quantum computing, because of the math, is, in fact, we double. So 3 qubits to the third is 8. And now it gets more interesting. All right, so the number of pieces of information, which I'm thinking of as the coefficients here, right, in my linear combination here, I have 8. If I have 10 qubits, I have 2 to the 10th, which is 1,024. So with 10 qubits all together, that's how many pieces of information I can store. And that's why with caffeine, I can go from this ridiculously large number, right, of bits that I would need to 2 to the 160. That's why it's 160. It's actually 2 to the 160 and grow. So the general pattern is 2 to the nth, all right? Our largest quantum computer is 50 qubits, right? It's not publicly available. We have the working prototype. That's the number down there. It's fairly big, but we can access that. Remember with penicillin, 286 qubits we would need. Well, by the time we get to a quantum computer, if we do, right, there's my lack of guarantee there, right, we will be able to access, while they are in use, right, once you actually get up and running, right, more information than there are atoms in the observable universe. And this ultimately will be considered a very small quantum computer, I think. How does this work? I don't know. Okay, that's quantum mechanics, right? And it's not only me, right? Another thing Richard Feynman said was, no one really understands quantum mechanics. Okay, so there are two principles, and without getting into them, we have talked a lot about superposition. This notion of, on one hand, with one qubit not just being 0 and 1, somehow being on the surface of a sphere, but also the way multiple qubits combine to give this explosive growth. The second interesting and weird property is entanglement. And this is where two quantum particles, whatever they may be, are so strongly correlated, no matter how far apart they are, that if you know something about one, a certain property about one, and you have to decide what you want to know, you will know the corresponding property about the other one. Einstein hated this. Einstein had a view that the world, the universe, needed to be very deterministic. And every time you ran an experiment, it should come up with the same answer. Unfortunately, he was wrong. And he helped science tremendously by trying to prove that he was right and failing. Okay, and other people stepped in. So entanglement, of course, with qubits, they're much closer. They're not across the Milky Way or anything like this. But this is one of these two properties, and this is what it means when Feynman was talking, to say, okay, I need to build a computer based on the principles of quantum mechanics. The gate set. So with a classical computer, the circuits at the lowest level are zeros and ones with ands and ors and nots and nands and things like this. At this level, we have qubits, and we have things like Pauli gates and Hadamard gates and things like this. Completely different set of how to do this. And they involve both of these. And algorithms especially involve entanglement. So the history of quantum computing really goes back to about 1900. Quantum mechanics picked up speed in the 1920s. And it proceeded through. The blue dots are things that IBM was involved with. I mentioned the 1981 conference. We talked a little bit about, well, some applications, some interesting things like quantum cryptography. I will hasten to say that quantum teleportation is not Star Trek. It means something completely different, unfortunately. Shor's algorithm, I'll take a moment and describe this. Peter Shor, then a mathematician at Bell Labs, now at MIT, produced an algorithm that was exponentially faster than any known classical method for factoring integers. Most people don't care about factoring integers, except if you're trying to break encryption that's assuming you cannot factor integers, particularly very large numbers that are the products of two primes, like RSA. And so hence, you may have seen articles about the impending quantum cryptographic apocalypse, because it's just horrible, right? Okay, so we have 50 qubits. The number of qubits like the ones we have now that you will need to break RSA is 100 million. 50? 100 million. Sleep well, okay? Now, there are steps we can do, but this is important about the small print. Okay, and then things have proceeded, and it's really been the last 10 or 11 years that we've picked up. So we've talked about qubits, but because these are physical qubits and because they have errors, they also have something called coherence time. A given physical qubit is not good forever. It sort of runs out of steam after a little while and starts to decohere. A qubit starts at 0, and then we do something to it. But after a while, you can't keep doing things with great fidelity after a while, so coherence time. One way of thinking about this is, let's say you brought up a photo on your phone, and it was a beautiful photograph, and after a while, you noticed some of the pixels started just randomly turning white, right? And more kept turning white, and eventually, if you waited long enough, they'd all be white. That point from the beginning to when they first start turning white, when you could depend on it, if you will, is the coherence time, right? And the same thing happens with qubits. So therefore, to measure the power of a quantum computer, you have to take into account things like the number of qubits, the error rates on individual qubits, the error rates on qubits that are working together, in particular for entanglement types of operations or C0 operations, coherence time, and several other things like this. This is called quantum volume. In the next month, we'll be publishing a paper about this. And in fact, this graph will change a little bit. This terrifies a lot of people who are making quantum computers. The quantum volume is a stress test to say just how stable will that machine be of doing every sort of thing a quantum computer could expect it to be. It's really hard to build a quantum computer. It's really hard. And just because you can build a quantum computer with n qubits does not mean you can easily build a quantum computer with 2n. All sorts of engineering and physical things happen in there. It does not scale linearly. And so, from our perspective, from the physics perspective, from the physics angle, is how well can we increase this quantum volume, and at what quantum volume can we do interesting things? And so that's the sort of work that we do internally. All right, so the IBM Q Experience is our free offering. On May 4th, 2016, we made it available to people. It was a very strange thing. Our CEO was on a plane to Japan, and we announced this, and we made it available, and she got wind of this, and she sent a very simple email, which said roughly, "What is this, and who said you could do this?" I will know by the time I land in Tokyo. And it was because we could, and it was a different way of approaching. It wasn't the methodical, big, bureaucratic way of proceeding through lots of things. And so quantum is very focused in this way, the way we structured this. In 1946, that was the ENIAC computer. When we first made the Q Experience, the 5-qubit machine available, that's what the microwave electronics look like. A little bit too close for comfort, frankly. But I got to tell you, maybe at this point, we've advanced to the early 1950s, relatively speaking. There is so much more to do, right? And of course, it's not just us who's going to do it. This is what a quantum computer looks like in the inside. You saw some of that in the video. That is the cryostat in the middle, showing some of the temperatures. Down at the bottom, it's between 10 and 15 Kelvin, so very close to absolute zero. Outer space, so if you find a nice, somewhat shaded place in outer space, is going to be about 2.7 degrees Kelvin. That's the cosmic microwave background radiation as translated to heat, right? So a quantum computer runs at a much colder temperature than outer space. I have lots of people asking me, well, can you just build them in outer space? I think they want spaceships, really. That's what they want, based on quantum computers. The chip itself, it's probably about that big, so what am I doing? Maybe 1.5 by 1.5 in size. They can get a little bit bigger, just the constraints of fabbing it as we create larger ones here. They sit on a printed circuit board. They are plugged in there, and then coaxial cables come down. So I'm going to show you a little diagram here. It's a little animation. All this does is shows you on a laptop on the left-hand side. Most of your programming today is going to happen on your laptop. You're going to be running Python programs. You're going to be using our libraries, right? And then you will issue a command that says, all right, run this on a quantum computer. So it will translate it into an intermediate form that is then run over to the microwave cabinet. There's a traditional computer sitting there. It will be translated into a series of microwave pulses of given shape, duration, right? That then goes to our model quantum computer over there. Something happens, it comes back, it gets translated, and you see the answer. This is a simple notion of, I simply want to measure the value of 2 qubits. So what I mean by that, going back to our sphere, right? If that's a qubit that's in use, when I measure, I am saying, I don't care where you are on the surface of the sphere, you must choose. Are you going to the North Pole or the South Pole? Are you going to 0 or 1? That is measurement. And how does it choose? You might say, well, if it's a little closer to the North Pole, it'll go there. If it's a little closer to the South Pole, it'll go there. Well, that's sort of true. What happens if you're on the equator? You get actually true randomness happening. So this is just a little picture here of showing the flow. This doesn't have to be your laptop. This could be something running in a container on a server or someplace. Okay, so now we're sending, these are the microwave pulses of a particular shape. Going in, this is a 5-qubit machine. It's targeting 2 particular qubits. It's saying, okay, measure and read out. And then it's coming back, remembering from close to absolute 0 back to room temperature through the microwaves, ultimately back to your computer. And like everything in computing, it ends up being a 0 or a 1. In this case, 2 1s. All right? So that's how it's all glued together. This quantum experience since 2006 has had over 98,000 people using it. They've run over 6.2 million circuits or experiments on this. Many of them have been working through the user guide. That is not necessarily deep, but they've been using it. However, there have been over 120 papers done by people other than us based on what they've learned on this in the last couple of years. And we go to a lot of different ways of making this available. Talia Gershon, a colleague of mine, did this kind of strange video for Wired where she explained quantum computing to a 5-year-old, a somewhat older, I think early teenager, all the way up to a professor of physics in different ways. And it's a lot of fun, right? You can see the model there in the background. This has had about 1.9 million viewers. So, are people interested in quantum computing? The answer is, given this 98,000, and given at least the numbers with this, the answer seems to be yes, right? So what we're trying to tap into is to show you how you can start using this yourself. She's also, as she quickly adds, she's received 2 marriage proposals as a result of this. She's married, though. On the Q Experience, for the 5-qubit machine, you can use a drag-and-drop environment. I highly recommend this. This is a good way of getting a feel for what quantum gates do, right? And so the gates are over on the right-hand side. You just drag and drop. There are videos or all sorts of ways you can learn to play with this. You can either then run it on a simulator or an actual 5-qubit machine. You can then see what the code is. Now, above the 5-qubit machine, you have to do some coding. And so our SDK is called QuizKit. It's written in Python, and it has everything you need to really start doing coding and writing algorithms. Now, we can't have people start from scratch every time, right? You can't do this at the lowest level. So we have something called QuizKit Aqua, which is a set of libraries on top. It really does 2 things. It encapsulates well-known algorithms that you can then use directly. You don't have to write them from scratch. But also, in application by application area, it allows interfaces to existing packages. So if you're a chemist and you want to use a Psi-4 model, you can do that directly. You can augment existing packages by using their models, running quantum calculations, and going back and combining with results from those other models. We can't rewrite everything just for quantum. If you're used to certain packages and software, you want to be able to supplement and not replace, and we can do that. We also have Tera, which is at the lowest level. You might be getting a theme here. Tera means earth, aqua means water. There's also air, and there's also ignis. So it's sort of one of these earth, wind, and fire types of, someone got creative. This is the very lowest level of how you would program this. Now above the free level here, we have the IBM Q Network. And the IBM Q Network is really our beginning way of saying, if you are really serious about this, if you are willing to invest in using this more, this is how you will get access to the latest and greatest machines, right? And so there are several models here. There are hubs, which I'll show you in a photo. We have partners, academic partners, members, and so forth. A hub is somebody here like Keio University. So Keio University has incredible academic depth in quantum physics and quantum computing. They are experts. We in IBM Research, unfortunately, cannot talk to every company in the world who wants to, at this point, go really deep. Also, most of us in Yorktown do not know Japanese. Okay? So Keio University is a hub. They have reached out. They have partnerships with these 4 companies, JSR, Mizuho, MUFG, Mitsubishi Chemical. They are working on quantum applications with Keio. Detail-wise, those companies pay Keio, Keio pays us, all right? NC State will get up and running. Oak Ridge, next month, Oak Ridge is already a hub. And various other ones like this. And there are all sorts of possible ways of doing this. If there is a university that wants to have a fairly high bandwidth connection with us, we can arrange that directly with us. There's a much more discounted way of universities working. Again, for these latest and greatest machines. If you simply want people to do some quantum computing in classes, by all means use the Q Experience. free Q Experience. If you want to do research and go beyond that, then we're talking this model. And so this is what hubs look like, as I've kind of described it with KO. Typically, a hub is a university, and usually it has some local clients with whom they're working. Partners work directly with us. All right, so I want to end here with the role of colleges and universities here in quantum. I've tried to be fairly straightforward with you that this is going to take a little time to really be commercially viable. Okay, there's nothing you can do today. The whole trick is to say, are we on the right track? From a hardware perspective, from a software perspective, from an algorithms, from starting to think about, well, this is the problem I'm worrying about. I know that I have done this, let's say, with high-performance computing, but these are the bottlenecks. Is it the sort of problem that maybe quantum is amenable to help solving? That takes time. So that's the phase, the so-called quantum-ready phase we're in right now. So if I tell you that it's going to take 3 to 5 years before we start seeing the real significant commercial uses of this, and if you happen to be in college right now, what will you be doing in 3 to 5 years, right? Wouldn't it be nice to be one of the first quantum experts? Wouldn't it be good and valuable and potentially personally profitable to be able to, right, step into with these companies that are starting to figure out how to make maximum use of this new technology? So for that reason, we very much care about this. And I talked about the next slide instead of this one. So let me jump back to research for a second. Sorry. Research, we can't do this all by ourselves. There are hundreds and hundreds of points where things can be improved. Every single little bit of this hardware. You take a big chunk of many different types of metals and freeze it down to absolute zero, you learn a lot about research. There are amplifiers, there are new topologies and architectures, and how you actually create these microwave pulses. In the United States, the National Quantum Initiative bill is probably likely to become law very soon. It was passed by the House of Representatives last week. It will be roughly $1.25 billion for quantum research over the next 10 years. All right, so from a research perspective, this is a good area to get involved with. So lots of things to be done here. And we can help, right? So we're always happy to talk to you. If you're applying for grants and so forth, you know, let's brainstorm. For people who are interested in getting into the very lowest level of how you manipulate and program these machines, there's OpenQuasm and newly announced OpenPulse, which really lets you describe exactly that microwave pulse which is coming down. So if you don't have several $1 million to build your own quantum computer, right? But you would like to do physics research at the pulse level of programming these things, you can use ours. And here's the specification. This is published openly. The actual spec, the code is all open source. It's under the Apache license, and you can visit this. So this is one way of doing research if you're not actually building hardware. Okay, let me jump back to education again. I arrived yesterday, by the way, from Poland late last night, so if I'm slightly out of order, that might explain why. So there are many places where quantum computing you can start to think about it and teach. Yes, you could teach an entire class about quantum computing, mixing it in with appropriate amount of quantum mechanics. No, you do not have to teach physics. As I've shown you a little bit, you can describe it all in terms of computer science and math. Now, there's the usual motivation of what do students need to know, what do they want to know, can they find jobs if they know this and things like this. But I believe there are many places across the engineering disciplines, some in computer science, certainly in physics, where you can supplement, even if it's a lecture or two, to say, and oh, by the way, in this emerging field of quantum computing, this is how it's done, right? This is the difference. These are the interesting open problems in this, of which there are many. Quantum computing, if it's nothing else, is probably going to be the source of hundreds of future master's theses and PhD dissertations, because it has opened up so many new areas, right, of how to do this. Even the things we think we know about, like compiling programs, right? The target for a quantum computer, not to mention the instruction set, is so completely different that there's great research. And to do that, you will have to combine many different areas to do it. It's not the straightforward way of doing it. So I started by showing you the most sophisticated computation centers. That was in the video. That's our model here that we show here. By the way, the reason why it looks gold is it is gold. Gold reflects infrared very well. And if you're trying to chill something down really cold, you want to reflect all that. The future computation centers, though, will look more like this. And the first time I saw this, I said, wow, that's really cool and kind of ominous, you know. Well, okay. Previously, you know, what I showed you was very industrial looking, and it's still state of the art. It doesn't look like a project in your basement, right? And IBM is a systems company, so we can bring together, you know, how to do power supplies, right? You know, these mundane things of actually building systems. The reasons why these systems are significant, and if you visit us in Yorktown in about a month and a half, you'll see one of these, is that in addition to the quantum computer itself, all the helium pumps and the electronics now are behind it, right? They're not kind of off to the side. So if you walked around it, you would see the panels with readouts and things like this. The cooling is a little different. So we're not just worried about the physics, and we're not just worried about building one chip. We are worried about everything, all the way up to what are the practical ways of building quantum computers, of installing them, of installing many of them. What are the engineering questions? As well as I've described, all the software, growing the ecosystem, what we do for education, and so forth. So I've been with IBM for 35 years, somehow. That just happened. This is by far the most fun and the most interesting thing I've ever done, because anything you're interested in the computer area, and you get to throw in physics and math and computer science and everything like this. Somewhere as we build out quantum computers, there's work to be done, right? And so I hope I've kind of given you a sense of that and maybe excited you a little bit about doing this. So thank you very much.
I think the IBM Q, and correct me if I'm wrong, that's a transmon charge qubit, right?
Yeah, it's a superconducting transmon Josephson junction. Yeah.
So if, that requires pretty complicated cryostat setups and is kind of confined to these data centers.
Mm-hmm.
If we were looking at the analogy of moving from like the Harvard Mark I to something that could fit in a smaller room that doesn't have cryostat, I guess, what is IBM's path forward that they envision for having, again, I guess a qubit that is more broadly scalable? I mean, like, maybe not everyone has a quantum computer in their homes necessarily, like replacing classical computers, but maybe that looks like a coprocessor.
Okay. Okay, so I can't repeat all that, but I need to repeat part of it. So what is our path forward from going through a 1,000-pound thing at absolute zero based on a particular technology to something where we can have many more of them that maybe runs at closer to room temperature and is more of a companion to what you do as opposed to something that sits somewhere off in the cloud? So there are multiple qubit technologies that are out there. So there are things like ion traps. There are some new things that people are looking at with photonics and things like that. There's some in silicon ways of doing this. Unfortunately, they can do 2 qubits right now. So scalability becomes a problem. And with almost every single technology that people are looking at qubits, and they do not advertise this, there's some number at which scalability becomes a really hard problem. And some of these numbers are shockingly low, like 10, right? And so when you look across, first of all, the different technologies, you have to kind of say, okay, well, you know, this looks more promising than this. And then some of them, they're almost praying that something happens because they don't know. You may know what I'm referring to. So we think that, first of all, this technology is probably the most likely to be scalable faster. We may get into an argument with the ion trap people, but so far, so good. From an IBM perspective, we are not saying we will keep with this technology to the death. We expect that, just like the rest of hardware, that it will be improved, it will be miniaturized. With this technology, we're not going to get away from the cold temperatures, so that will be an issue of how we do that. I'm not going to make one of the Thomas Watson sort of predictions. I always forget the number he said, but like, the world needs 5 computers or something like that. You know, he said this. So I won't make that prediction. It's not clear that being on the cloud is any sort of future hindrance, right? Just thinking about the ways things go. You're not going to want these in your car, let's put it that way, right? So we'll see, right? In the foreseeable future, they will be cloud-based. When you, just as an example, let's say I want to change the payload. So I want to change the quantum device at the beginning. You have to slowly warm this up to room temperature, which takes at least 24 hours. Do whatever you're going to do, and cool it down again, which takes roughly 36 hours. So, and then test and do these things. So you're probably talking about a minimum of 4 days if you need to bring this down. Also, I think rapid changes will be done year to year. So you probably don't want to buy one. I mean, that's fundamentally, right? You probably really want to pay for the quantum access and the power, but owning one, within 3 years at some point, you're going to have a very nice antique, right? So much to the extent, you know, this one that we have over on the left was the first model we built. I'm strongly considering donating it to the Smithsonian, okay, as the first, you know. So think about that, you know, for ownership. So there's going to be a whole bunch of normal things that happens because that's what hardware people do. And then there's going to be some incredible breakthroughs. And it may seem weird, but I do believe that people will use quantum computers to create new materials to make better quantum computers. Talk about no guarantees, but yeah. So.
What's the relationship between what you do here and eBay?
Completely different. Much better. Okay, so, no, so I was joking with that. Okay, sort of. So D-Wave has been around since the early 2000s. D-Wave does simulated annealing, which is a particular optimization technique, but with quantum computing, all right? They employ thousands of very poor quality, hardly entangled qubits at all to do something. They have never shown that they can do anything substantially better than what you can do using classical methods. Fujitsu has produced an FPGA-based quantum-inspired annealer, which supposedly done the same thing that D-Wave does. What we are after is producing a universal quantum computer. That means that the instruction set is universal. It essentially becomes a quantum Turing machine, and that's what we're building. D-Wave is not a universal machine. D-Wave will not be a universal machine unless they radically change their architecture. So they are a specialized optimization machine. If that does good by you, great, but no one else is doing that. Everyone else is building universal quantum machines. So
let's continue the conversation at a reception in Alexandria, and you will join me in thanking Dr. Sutor.
thank you. Oh, thank you very much.